Now in this question, we are also doing a paper 1 question. I actually think it's actually a very easy question, but most of it comes from grade 11. Now remember, when things come from grade 11 and you're in grade 12 and you are struggling, you need to go back to the foundation, actually look at it and then come back. So let's see what the question is and then I'm going to elaborate on it. So this is a question 7. It says the diagram below shows 2 small identical metal spheres which are named R and S. Now remember, if the examiner has named it R and S, you stick with R and X. Don't say sphere 1 or sphere 2. And they are each placed on a wooden stand. Now remember in grade 10, this is actually an experiment we do in grade 10 when we start with electrostatics. Now sphere R and S carry charges of positive 8 and negative 4 respectively. We must ignore the effects of air. I just want to elaborate on this question. In grade 10, you were introduced to electrostatics and they said these 2 spheres come into contact with each other and then they move apart. And then we had to calculate the new charge, also had to calculate the number of electrons that were actually transferred and so forth. When we got into grade 11, things got a little bit tricky. We started learning about the electrostatic force and then the electric field and so forth. They also started putting them in 2-dimension and then 3-dimension and so forth. And then in grade 12, they actually add everything from grade 11 and grade 10. So make sure if you are not really sure, go back to your grade 10 and your grade 11 book. Another thing that you guys need to remember that is very crucial in grade 10 is you need to learn your conversions. Remember what I always say, physics is a language and we must all speak the same language. So sometimes you need to convert things first before you can actually use them. For an example, when we talk about the mass of something, we use kilograms, we don't use grams. When somebody's baking cookies, we use grams, right? But in weight, we use kilograms. If a car is moving, we use velocity. Even though we can talk about kilometers per hour, we use velocity. It's exactly the same thing when we talk about charges. We do have nanocoulomb and microcoulomb and all that stuff, but we need to speak the language of coulomb, which means if you are not given it in coulomb, you must first convert. The sad reality about it is that it is not on your formula sheet, so it's something you need to know off by heart. So what I would suggest to all the grade 10s that are still watching, you need to master this in grade 10 so you do not actually have a problem in grade 12. So let's look at the diagram that we're given. These are my 2 spheres. I've got R and I've got S. I can see that one is a positive, one is a negative. Just to elaborate further, if we've got opposite charges, they will attract, like charges will then repel. So let's see what the question says. It says, explain why the spheres were placed on a wooden stand. And this is only for 1 mark. Now, I just want to elaborate on that question further. Now, remember, guys, some objects are actually conductors of electricity or electric charge, and some metals are insulators of electricity and electrical charge. Now, in grade 10, we did this. We looked at plastic, we looked at wood, we looked at water, we looked at a number of things to say what was insulators and what was conductors. Now, placing something on the wooden stand, wood is actually an insulator. So when we place a stand on a wooden stand, it doesn't actually let current flow through. But now they want us to explain that is actually only for 1 mark, so that is not too hectic. So in explaining 7.1, you could have said this is to ensure that none of the charges are lost, to ensure that charge does not leak. Now you can't really say electrons because remember a movement of electrons is then charge and it doesn't leak to the ground. So that's what we could have said in explaining this question. Let me just write 7.2. So let's see what the next question has for us. Now they are continuing to say that sphere R and S are brought into contact for a while and then separated by a small distance. Now we need to calculate the net charge on each sphere. Now remember, when we have one sphere that is positive, one sphere that is negative, opposite charges are like, oh my word, I'm so attracted to you. And then they attract because one is a positive and one is a negative. And as they're attracting, they don't really change the number of electrons, but they will both have a new charge. Most of the time, they will both have the same charge and then will then go, and then they will start repelling. Right? So now we need to calculate if they come into contact for a while and then they move apart, what is the new charge that each of them are going to have? Remember, if you rub yourself and you touch somebody, there's a little spark, right? It's something like that. So let's see, we need to calculate the net charge. Calculating the net charge is grade 10 work. So you can say Q net. Remember, net in physics is like total or the sum of. Remember, charge is represented by a capital Q. We are talking about sphere R plus the charge on sphere S. Remember, we can't say 1 and 2 because the examiner has already named it for us. I'm going to say 2. Remember, R is an 8, if I'm not lying. Yes, R is 8. The other one is a -4. So I'm going to say 8 plus, open bracket, minus 4, all over 2. So let's see what we get over here. I can actually do that in my head, though. Yeah, let me just not waste time, do this in my head. I'm going to say 8 minus 4, I'm going to get 4, divide that by 2, I'm going to get 2. They used this to measure. Remember, they just wanted the new charge of it. So this is mute coulomb. It's not converted yet. If you're still struggling with that, that is then grade 10 work. The next question says, I must draw the electric field pattern due to the two spheres of R and S. Now look here. It says, of the two spheres of R and S. This means the new one. And when we talk about the electric field pattern, we must say how the electric field is actually going to move and so forth. Now remember, here we just calculated that both of them are going to be positive after they touch and then move back together. I'm just going to say 7.3 here. Now, meaning that both are going to be positive. Now we know that when like charges come together, they're like, oh my word, and then they repel. Unlike charges are like, yes, and then they will attract. Right, so now that they both are positive, it means that we have a little bit of a problem. So I'm going to have a positive one there. I'm going to have a positive one there. You could have named it, let's just stay consistent for the examiner's sake. Let me also name it Q and R. Let me name it R and then S. Now remember, they're both positive. Just want to draw something here quickly. Remember, if it's a negative, if it's a positive, the examiner is looking at the field lines. From the negative, it goes into the negative, but a positive, it goes into the negative and it goes out of the positive. Yes, it will go out of the positive. So if they're both positive, it means they will repel and then this one will move like that. That is then how they will look. And I'm going to tell you what the examiner is actually looking for in a drawing like this. Because they're both positive, they are repelling and they look like little jellyfish manikis here. Because they don't want to touch, because they are like charges. Now, I just want to write for you guys. Now, I want you to have your pen here and tell you, so you actually write these notes. This is what the examiner is looking for. The first thing they are looking for is the correct direction. The correct direction. Direction in a sense that these lines, remember, if they're both positive, they must move away. If they were negative, then they would move towards. So they're looking for the correct direction. And then the shape of the field lines. The field lines. I'm going to draw one in blue just so that you don't do this. You can't have a field line that looks like this and say, oh, but it's going away. No, the examiner is not looking at that. They are looking at consistency. We have no field lines crossing. Field lines crossing. This means I'm also going to use a blue one. You can't have one come in straight, but then they are crossing. The examiner doesn't want that. You cannot have them crossing. And the last one, no lines inside the sphere. So these are most of the things that the examiner looks for. Otherwise, you're going to have your full marks. This means if you have a line, don't have one in there and then say it's going out. So all the blue is wrong. Not inside the line, not inside the sphere. It should have the correct shape and no touching or crossing of field lines. Field lines can never cross. That is not true. We don't do that. And then I think this question was for 4 marks. It was for 3 marks. If you can do all of that right, then you've got your 3 marks into the bag. So let's look at what this question continues to say. Now they're saying, after R and S have been in contact and separated, remember they're now positive, a third sphere, which is now T, this is the one over here, of charge 1 positive. So now we've got a positive, and a positive, is now placed between them as shown in the diagram. I just want to elaborate on something a little bit here that the examiner also loves catching you guys on that you guys don't notice. When we talk about distance in physics, we talk about meters. So first things first, you need to divide this by 100 to actually get it into meters. We don't talk about centimeters. The language of physics, you always have to talk about meters. That is then the consistency. So now between these two, they are placed apart at different distances. This R is a positive, T is a positive, and then S is also then a positive. Now 7.4 says, draw a free body diagram showing the electrostatic forces experienced by T. So you start at T due to R and S. I want to go just highlight this one. Free body diagram. Free body diagram means the object in question turns into a little dot. This is 7.4. I'm going to do it the long way around. I'm going to show you how I do it in my classroom. 7.4. If you have R on this side, we have T, and then we have S. I always say to my kids, put it on T. Remember, they're all positive. If my dot is on T and then R decides to come along, what is T going to do? Positive, positive, and positive will repel. T will go, no, I'm running away. I go back on T. If S decides, I want to move closer, what is T going to do? A positive, and T will move in the opposite direction. Now they say free body diagram. T will become a dot, and then remember, vector diagram, I'm going to have two arrows showing the directions. But what arrows are this? This will be the force on R on T. Let me just use a capital T for consistency of T. In this direction, this was the force of S on T. That is what the examiner is looking for. This is what you're going to get marks for. You're going to get a mark for your circle, naming your forces, and actually showing them that they are going in the right direction. Remember, if you are struggling, I always say go to the diagram, ask yourself, if this one came, what's the other one going to do? And this was just for 2 marks. Let's see, number 7.5 says calculate the net. Remember, the word net means total in physics. Electrostatic force experienced by T due to R and S. So what are they telling us? Just want to erase all of this. They are telling us, okay, here we have put T into question. How is this one affecting T and how is this one affecting T? Now remember, we calculated that the new charge of R was 2 mu C and of S was also 2 mu C. Electrostatic force due to T on R. Let's calculate what we're going to have there. That is then 7.5. So I can say the force of S on T, I can say Q1 over Q2 all over R squared, right? Now, an interesting thing with this question is that remember that these two are actually then equal, right? They have the equal same number of charges. So that actually made it simple. And I know that K in this formula is a constant. This you're going to get on your formula sheet, which is 9 times 10 to the exponent 9. I always say put conversion factors. Now remember, I just want to go back here so that you know where I'm getting it from. They told us, let me just find it quickly. They told us that 1 is mu C. Converting this to Coulomb, I'm going to say 1 times 10 to the negative 6. Converting this to Coulomb becomes 2 times 10 to the negative 6, as well as this one, it becomes 2 times 10 to the negative 6. You need to know your conversions of your hearts, my darlings, unfortunately so. So the first charge, and that is on T, that is 1 times 10. Oopsie daisy, what did I do here? Let me just undo. There we are. This is 1 times 10. That is negative 6. And then here I'm going to have 2 times 10 to the negative 6. And now we have to look at the distance between S and T. We were told it is 20 centimeters. But remember, you must always say 20 divided by 100 to get it to meters. And remember, that is distance squared. I'm going to put it exactly as it is in my calculator. Remember to always use brackets so that you can get a correct answer. I'm going to say 9 times 10 to the exponent 9. Close my bracket. I'm going to have 1 times 10 to the exponent, let me just backspace, to the exponent negative 6. Close that bracket. And then next to that I have 2 times 10 to the exponent negative 6. Close that bracket. At the bottom, I'm simply just going to put it like this. I'm going to say 20 divided by 100. Close my bracket, and that is to the exponent 2. And then I get 0.45. And remember, Let me just write it down, 0.45. The SI unit for force is then newtons. Now we were talking about S on T. Remember, S is moving to the other side. It's moving in that direction. So that is to the left. That is then to the left. Let's look at the next question. See if we can't squeeze one more. So now here we drew the free body diagram. We'll calculate the net on T due to R and S. Let's look at 7.6. It says define the electric field at a point. Now, I always tell you guys, with your definitions, you cannot fail them, because if you technically calculated or counted, all the marks for definitions are actually very substantial marks you guys can use to get a level 7. You cannot fail because you are lazy to read. Remember, have a little booklet where you read and write them daily so that you do not forget them. If you are a little bit forgetful like myself, always use a formula to refer back and then you'll never forget it. Let's light number 7.6 quickly. Define electric field at a point, which is 7.6. It is the force experienced. Remember, no slang, no shortcuts, no mixed or WhatsApp language. Force experienced per unit. Positive charge. Charge placed at that point. And you were going to get full marks just for writing this. Let's look at this question. Let's see if we do have time. And then 7.7 says we must calculate the magnitude of the net electric field location of T due to R and S. Now, a question like this, my darlings, it's actually very, very simple, but this is what needs to happen. I'm going to use this diagram here. Remember what we said? If S came towards T, T would move in this direction. If R came towards T, T would then move in this direction. What you need to calculate now, or what you first need to do, is make one side a positive, one a negative. Remember, when we have forces in opposite directions in physics, one must be a positive, one must be a negative. If something moves up, it must mean that something must move down in the opposite direction. So this means finding the net electric field, you can say E of R, you can say Q over R squared, and on this side you're going to do the same thing, Q of S, you can say Q of R squared. Now, choosing one side as a positive, meaning you're going to actually subtract the other negative from the other side. Unfortunately, we did run out of time today, but if you do look at this question, you look at the net. Okay, I'm actually told I do have time, so let's push this question quickly. So that is 7.7. So I'm going to start with R. So I'm going to say E of R. I'm going to say Q over R squared. Remember, K is a constant. That's 9 times 10 to the 9. The Q of S was 2 times 10 to the negative 6. That is all over R. Let me just summarize it in. The distance between R and T, that was 10 centimeters. Converting that to meters gives me 0.1. I'm just going to give you the answers already. So if you are doing this question with me, make sure that you do get the same answer as myself. If I look at the electric field of S, remember we've got Q, KQ over R squared. K is a constant, which is 9 times 10 to the 9. And the charge on it was 2 times 10 to the negative 6. Remember, that was 20 centimeters. Converting it to meters gives me 0.2 squared. And I get 450,123 NC1. Now, E net, I've chosen this one as a negative because I chose that side as a positive, this side as a negative. E net will be the electric field of R plus the electric field of S. E net, this one will be 1800,123 minus, this is plus 450,123. So the E net will give me negative 1350123. I'm going to teach you guys something here. I'm going to move my comma. 1, 2, 3, 4, 5, 6. I'm going to put a comma there. This technically then becomes negative 1.35 times 10 to the 6. And that is N dot C1. And that is to the right. Remember, I took the negative as the other direction. So I can remove my negative by putting it to the right. And a question like this, you can then get full 6 marks for it. Remember, the examiner wants to see that you've chosen direction, that you know that there were opposite forces in the different direction, and also giving a direction for your final answer.